But basically, when we're talking about probabilities, we're trying to answer the question of what are the chances that something is going to happen? Now, probabilities are used in calculating insurance costs. They're used in athletics. They're used in picking which route you're going to take to work. They're also used in a lot of other games and things like that. But probabilities, we actually, without even realizing it, use on a day-to-day basis just to make simple decisions. Which one of these strategies is going to give me the best possible chance for success? All right, two different types of probability. One is empirical or experimental, okay? This is an inductive process. It's an inductive process, meaning that we're going to look at a lot of events that happened in the past, and then we're going to try to use that probability for future events. The police can look at the historical data, okay, how many accidents have we had, how many can we expect in the future, and then two, they can also use, kind of going along with that, they could say, okay, this city had a similar intersection or something that had a lot of trouble, let's see how they fixed it. And then they can predict, hey, doing this will decrease it a certain amount. It's used in baseball a whole lot. If you watch a game, towards the end of a game, you'll see them switch pitchers. You know, sometimes 3 batters in a row will face 3 different pitchers. Okay, and that's because historically maybe that batter has faced this specific pitcher and hasn't gotten a hit on him in 10 at-bats. All right, so they say, hey, this batter really struggles against this pitcher, so we're using that to say the probability of him getting a hit this time is very low. That's empirical or experimental probabilities. We are going to be using a lot of another kind of probability, and that's what's known as theoretical. Theoretical probability is more of a deductive approach. Here, we're starting with certain given information, and we're trying to then apply it, okay, and be deductive. We're using a logical train of thought to calculate a probability. This would be like, for example, if we're throwing something at a target and it has a bullseye on the target, we could calculate the theoretical probability of hitting the bullseye by simply taking the area of the bullseye and dividing it by the area of the entire target. The last thing I want to look at is the concept of sample space, and we're going to spend a good amount of time talking about this. Sample space in an experiment, which an experiment is just a situation that we're working with probabilities in. It doesn't have to be a scientific experiment. Okay, but the sample space is all the possible outcomes in a certain circumstance or in an experiment. Each outcome of the experiment corresponds to exactly one element of the sample space. Okay, so you can't have more things in your sample space than you have possible outcomes. However, the number of elements in the sample space is not always the denominator of our formula for probability. All right, so let's talk about getting a sample space for a problem. And let's say, for example, we're going to flip a coin 3 times. So we'll keep a simple concept for the moment. One way we can determine a sample space is by finding a tree diagram. In a tree diagram, what we do is we outline the possible results. So we're going to flip a coin 3 times. On the first flip, we could get heads or tails. On the second flip, we could get heads or tails. And on the third flip, we could get heads or tails. But if we're finding the sample space, we need to trace all the possible outcomes of the 3 flips. So, for example, we could get all heads. Okay? Or we could get 2 heads and a tails. But that can happen multiple ways. Okay? There's only one way to get all 3 heads. Okay? But watch this. We could get head, head, tail. Alright? 2 heads and a tails. Or, look at this. We could get head, tail, head. But we still got 2 heads and a tail, right? Okay? So there's 2 ways of doing that. There's 1 way of doing that. We could also get head, tail, tail. So head and 2 tails. Okay? Then if we go down this branch, tail, head, head. 1 tails, 2 heads. There's another way of doing that. Okay? Or tail, head, tail. 2 tails and a head. There's another way of doing it. Okay? Tail, tail, head. We have another way of doing that. Or all 3 tails. All 3 tails. And there's only 1 way to do that. So, our sample space is a set. Okay? It's a set of possible outcomes, and those outcomes have to be unique, though. What we end up having here is the set of all unique things, but we also, once we start getting probabilities, we have to consider how many different ways could each of those outcomes occur. And that's where the counting principles that we learned last week will come into play. On these, the order doesn't matter. So it's a combination. One other way that we can determine a sample space, though, that's particularly helpful when you have a number of choices for 2 variables or 2 events, is making a table. And the most common of these is rolling 2 dice. Okay, you roll 2 dice, you're going to get a 1 through 6 on the one and a 1 through 6 on the other. Okay, so if you're adding them up, if you've ever played a board game, you've rolled 2 dice before. Okay, you're going to get a 2 or a 3 or 4 or 5 or a 6 or 7 or 8, 9, 10, 11 or 12. That's not all the possible ways the dice can fall. There are 36 possible rolls, but that doesn't mean our sample space has 36 elements in it. Okay? What would our sample space be in this case? It would be 2 through 12. Now, again, like we had with the heads and tails one, that doesn't mean all of these are equally likely. Okay? How many ways can you roll a 2? There's only 1 way to roll a 2, right? You have to get a 1 and a 1. There's only 1 way to roll a 12. However, to get a 3, you could roll a 2 with 1 die and a 1 with the other, or you could roll a 1 with the first die and a 2 with the other. So there's 2 different ways. There's 2 possible ways of getting a 3 or an 11. Alright? Which is the most commonly rolled one,
6 or 7.
theoretically?
7.
7, okay? There are 6 different ways of rolling a 7. There are only 5 ways of getting a 6 or 8. There are 4 ways of getting a 5 or 9. There are 3 ways of getting a 4 or a 10. You see here, the probabilities are different. By the way, this is why in some board games that you are rolling dice, sometimes unique things will happen when you roll a 7. Because 7 is the most commonly, theoretically, 7 is the most commonly occurring one. Or, well, think about how many different ways can you roll doubles?
6.
6 different ways, 1s up through 6s. So, Monopoly, if you roll doubles, you get to go again. That's going to happen 1/6 of the time, theoretically. 6 out of 36 of the rolls are doubles. That's how you get out of jail, that's how you get to roll again. Monopoly uses it too. Now, let's just talk through a couple of these. We won't get through all of them, but let's talk through a couple of these. If we have a coin and a 6-sided die, this is one where the table would be helpful for us. Okay? So we have a coin, which means we get either heads or tails. And then we get a die, so we have 1, 2, 3, 4, 5, or 6 for ourselves. Okay? So a head and a 1 or a head and a 2 Okay? That's part of our sample space. The rest of it would be a tail and a 1, a tail and a 2, a tail and a 3, 4, 5, and 6. Now we would want to list those in the braces to express it as a set, but that would be our sample space. Okay? Another case like number 3 here. A taste tester has to rank 3 varieties of orange juice. Okay? A, B, and C according to preference. So what's one way he could rank them?
CBA.
I heard ABC and I heard CBA,
ACB.
ACB, CAB, BCA. Do we have them all yet? No? There's one more. BAC? Yeah, there we go. Now guys, think about this please. What are we really doing here? It's a permutation. We're finding all the permutations of 3 items, A, B, and C. Here, this is a case where our sample space, the order matters. Okay, because if it didn't, we'd only have one thing. Because we're using the same 3 every time. 2 marbles are selected without replacement from a set containing 2 reds, 2 blues, and 1 yellow. The color of each one is recorded. So if I'm picking 2 out of there, what could I get?
2 reds.
2 reds, 2 blues. Could I get 2 yellows? No. A red and a blue. A yellow and a blue. And a red and a yellow. Okay? So look, there's our sample space. There's only 5 possible outcomes. Now, number 5, think about this one. 2 county supervisors are selected from 5 supervisors. If I wanted to figure out how many I could have, it's a combination. 5 choose 2 would be my combination. So, that's the idea here behind finding a sample space.